Hello everyone, I welcome you to today's presentation, and which we are going to cover geoelectrophoresis. So earlier on we discussed and we defined what electrophoresis is. So today we are going to move a step forward, and of which we'll try now to understand geoelectrophoresis, of which it's a form of electrophoresis as we mentioned earlier. So let's all have in mind to say that when it comes to geoelectrophoresis, we are dealing with a method that we can use. So a method we can use to separate proteins based on their sizes. So basically we are dealing with proteins, separation of proteins or purifying of proteins, but now we are focusing on what? Their sizes. So another method we can use is um, geofiltration chromatography. So we can also use this method. But now, when it comes to geoelectrophoresis, our main focus, or we are using electric field. So we are going to apply electric field uh, on um, uh, on the apparatus, and when that is down, the electric field now will bring about proteins moving down the gel. And when that happens, the proteins now will be moving at different rates. So what are we talking about here? They've mentioned different rates. So the different rates, this implies to say that depending on the size of the particle, the movements will differ. So if smaller molecules are present, they'll be moving alongside, and then those that are a bit bigger will be lagging behind. So what we need to keep in mind to say is that the movement of particles will be at different rates. So that we should always keep into mind. Okay, so now when we are mentioning each and every time we are dealing with geoelectrophoresis, we should always have in mind to say that there is electric charge that is being applied at a certain point. So the gel as a supporting media for separation of, maybe for example we're talking about the DNA or the RNA or the proteins, they are influenced by electric charge. So once that electric charge has been applied, that's when we are going to observe to say that, oh, there is this separation of what? Of proteins. So the technique by which now this will be happening is what we call molecular sieving. The sieving, I know we've used a siever before. So molecular sieving technique is what is used when it comes to geoelectrophoresis. So this gel acts as a what? A molecular what? Material. So when we are comparing this gel to a sieve, we are saying to say that it's supposed to be porous. It's supposed to have what? Certain pores, and of which those pores will be allowing molecules to be moving. So under the influence of what? Electric charge, oh, electric field, and we've also discovered something new to say that they have what? They have pores. So it is important for us to note to say that the gel is supposed to be neutral. It does not supposed to have any charge with it. Each and every time we are dealing with a gel, it's supposed to be neutral. So now, different types of gels can be used when we are doing gel electrophoresis. So now, depending on the type of the gel that is being used, and then the name will change. So for example, we are using agar and agarose. So in this context, the name of the electrophoresis will be agarose gel electrophoresis. If you are using starch electrophoresis. If you are using polyacrylamide gel, that will change now. It will be polyacrylamide gel electrophoresis. So just simple as that. So remember the last point, which is saying to say a porous gel act as a sieve by retarding, or in some cases by completely obstructing the movement of macromolecules, while allowing smaller molecules to do what? To migrate. So basically they are trying to tell us to say that if we have different sizes, those smaller sizes will be moving freely, and those molecules that are bigger, they will be at least something like an obstruction by the pores that are found in the gel. So that's what basically this implies. So now, when we are dealing with gel electrophoresis, it has a principle under which it works. So the principle of electrophoresis, it's based on what? The electromotive force, the EMF. So the electromotive force is generated across the electrodes. So as we go on, we are going to see the diagrammatic presentation on how that happens. So it's generated across the electrodes, and it pushes or pulls the molecules through the gel. So once that field has been generated, it's the one now that will be involved in terms of pulling or pushing the proteins across the what, or through the what, the gel. So now here is what will be the how the movement, the molecules will be moving like. So we are talking about the electrodes. We are expecting to have in mind the positively charged particles and the negatively charged particles. So basically what will be happening here, since we are having the positively charged and the negatively charged uh, electrodes, so we're expecting now the proteins, if we're having the positively charged proteins, they'll be moving towards the negatively charged electrodes. When we are having a negatively charged protein, it is going to be moving towards the positively charged electrode. So that's how now the movements will be like. So now, when we're talking about the the gel electrophoresis, so this can be carried in two methods. So we have the first one, which is the vertical method. The vertical method, and the second one, it's the horizontal method. So now when we talk about the vertical method, I'll give the best example is the SDS page. So the SDS page, which we can use when we want to separate proteins, and the horizontal gel apparatus, it is used for immune electrophoresis. We can also use it for isoelectric focusing and the electrophoresis of DNA, RNA in the agarose gel. So we should also note where we can use the horizontal and where we can use the gel apparatus, and what we can use it for. So basically that's what we are supposed to have in mind at the moment. So now, okay, here is just a brief diagrammatic presentation on how the electrophoresis works like. So imagine this is the diagram, the diagrammatical presentation on how electrophoresis is supposed to work like. So we'll briefly maybe try to, I'll briefly try to explain and see how it is being done. So as you can see downwards here, these are positively charged. These are positively charged, and on top here, negatively charged. So we've connected the power source, which is giving the electric field to the slab. So once that happens, we've connected in such a way that on top it will be negatively charged, and at the bottom it will be positively charged. So now notice one thing. Here is what we are having. We are having more like wells on top here. So these are wells. Here, as you can see here, these are wells. Well, 1, 2, 3, and 4. There are 4. So this is number 1, number 2, 3, and number 4. Okay. So now, this is how it works. Once we put a protein in here, inside here, so mind you, we are having more like this this protein or a substance which we've put here. Maybe let's say that we've put on number 4, we've put here, and then we've connected this to the power source. Electrophoresis now has started to take place. So inside here we are going to have a porous gel. So we are going to get just a bit of this diagram with more like we zoom it, we see what happens inside. So inside there is a porous gel, and this greenish substance we're able to see here, this is representing a protein that we've put, and the porous gel. So the gel is supposed to be porous to allow now for this protein to do what? To be moving downwards. So if this gel was not porous, it won't be possible for this protein to do what? To move downwards. So now, as this protein is moving downwards, we're expecting some forces to be acting on this protein, of which we have three proteins that are supposed to be acting on this protein. The first one is the gravitational force. The second one, we have the frictional force, and we also have the electric force. But now the gravitational force is not that much because the velocity here is constant. So when the velocity here is constant, the gravitational force is equal to what? 0. Because we also know to say that gravitational force is can sometimes be referred to as what? Acceleration. So now, here is what happens. The friction force is more like the opposing force. It is opposing the motion. So that's why if you've seen downwards here on this green, which is a protein, of which we've just gotten from this main diagram we are seeing here on here. So this is the protein that we've gotten, and we've put it here. So now we are trying to demonstrate on how now these two forces they work on this protein. So we're having this frictional force which is pulling this protein upwards, as you can see, and then we have the frictional force, the electric force, which is pulling the protein what? Downwards. So we are going to write the electric force. It's going to be represented by EF, and then the frictional force we are going to use FF. So now we need to have in mind to say that there is velocity. There is velocity somewhere. So let's now try to determine the velocity that is there. We try now to determine the velocity at which this molecule will be moving. So that's the thing. So mind you, we are talking about the force that this object or the protein that is in our electrophoresis device, uh, it is being affected by various forces. So if we want to find the velocity, we are going to come up with a formula from the force, the forces that are working on the on the protein. So we also know to say that the summation of the forces working on this protein will be equal to mass multiplied by the what? The acceleration. So in this case, the acceleration is what? Is 0. So if you multiply the mass multiplied by the acceleration, which is a 0, the answer we are going to get here is what? A 0. So here is now what is going to happen. We are going to have the summation of force, which is this, the summation of the forces will be equal to 0. Okay, so now the summation of these forces will be equal to 0. So now again, we know the forces that are acting on this object. These forces, we know them. So since we know these forces, what are we going to do at the moment? We are going to get those forces, and then we put where the summation of these forces is. So remember, we said to say that the frictional force, it's the opposing force. So it is the opposing the motion of what? The electric, the movement of the protein. So since it's the opposing force, it will be negatively charged. So this is the more like the supporting force. So this will be what? Positively charged. So now we are doing the summation. So now let's add. Will be electric force minus frictional force. Why have we put a minus here? So imagine maybe it was like this. Okay, let me just try to erase something here so that at least I use the board a bit. Okay. Okay, hopefully now won't be able to forget what I've erased that side. Okay. Okay. So remember to say that we have our negative, the positive one, which is the electric force, which is the positive one. So we are saying that we are adding. So the electric force plus the negative friction force. So we are going to multiply there. So remember, rules of mathematics, indices, positive multiplied by negative, what will be the answer? The answer is negative. Hence, us writing it like this, electric force minus frictional force, which is equivalent to what? To 0. Okay, now from here, that's where now we are supposed now to move a step forward. Allow me again to erase that so that at least I use the board a bit. My cupboard is too small, forgive me for that. Next time I will make a presentation like this. I'll try to put a board, a big board, so that at least I use it for other things, unlike what is happening at the moment. So at this point, allow us now to employ the principle that is that falls under electromagnetism. So when we are dealing with electromagnetism, when we're having an electric field that is constant and working on a charge, we know to say that we can find the forces by implying the formula I'm about to write. So that implies to say that the E, where is the marker? Okay, just a bit. Okay, so from electromagnetism, we know that if we have a charge inside the constant electric field, the force will simply be the electric field. So the force, now we are trying now to determine from here. Remember, we are still here. So we have the electric force. So now we are trying to determine how can we solve for the electric force. So this electric force, remember, is being applied constantly. So if the force is being applied constantly, how can we maybe find the value of the force that is being applied constantly there? So now, what we are having in mind is this now. So we are going to find that force when we get the electric field that is being applied on that device. We multiply by the quality of the charge being applied to the device. So this is what we are going to use. So this one, we are going to get it, we replace where we've put the fe. So if we do that, this will become a z eq, where the E is simply the electric field and the Q, it is the charge that is being applied to the device. So that's the principle or the rule number 1. Okay, so how about now the frictional force? How can we find the frictional force? So we should all have in mind to say that the frictional force is a drag force. Now from your physics, always we can find the drag force when we get the coefficient, which is going to be represented by the small f, the coefficient friction, and then we are going to multiply by what? The velocity. So the coefficient friction multiplied by the velocity is going to give us what? The value of the drag force. So we are going to get this and we put it where we've put FF, the symbol for what? Frictional force. So once that happens, we are going to have this, the FV. So now we are having this as the formula. So now here is the thing. Our aim is to determine how can we find the velocity of the protein that is being, or the substance that is in our device. So for us to do that, we are going to make V, this V here, as the subject of the formula. So when we make V as the subject of the formula, here is how things will be like. This negative FV, it's going to cross the equal sign, and once it crosses the equal sign, it becomes a positive FV, the positive FV. So once it becomes a positive FV, so the equation now will change from the way it is like this. It will be EQ will be equal to FV. So now if we want now to find the value of the V, this, it's simple. All we need to do at this point, we just divide by what? By the F, and here we also divide by what? By F. Hence us coming up with this formula as the velocity will be equal to EQ over F. Please, if you have any questions from what I've explained, you are free to ask. Feel free to ask. I will be more than glad to respond to your questions. Okay, so now from here I know to say that we can now come up with a certain conclusion from here, from what we've just discussed, or just from the equation that we've formulated downwards here. What are those things? Let me try to highlight on those important issues that were raised as we were trying to come up with this equation. So now here are the things. When we are trying now to determine now the velocity of a protein, this now will be affected by some of the factors, and of which those factors will be: number one, the electric field. This is our electric field we're talking about. Number two, the charge of the molecule. Remember we talked about the charge that is being applied. And the coefficient friction. So the friction that is being produced when this porous gel here is opposing the movement of this protein, it will bring about affecting the velocity. So if the friction is too much, meaning we're expecting this protein to be moving slowly. When you apply a electric charge, so the amount of electric charge that is being applied will affect the movement of what? Of the protein. Also, we are talking about the charge. So we will soon understand why and or how those charges will actually affect the rate, the velocity of a substance. Okay. So okay, basically this is what I was trying to imply. So the statement reads: from the equation, so the velocity, so this was supposed to be the velocity at which the protein will be moving down the gel, depends on the one, electric field strength, the charge of the molecule, and the coefficient friction. So sometimes we can ask to say, which of the following cannot affect the velocity of the protein, the moving protein? In electrophoresis, we'll put options. Is it A, electric field strength, B, charge on the molecule, or C, coefficient friction, or D, none of the above? Obviously we are going to go for the last option, which is the D. Sorry for that. Yeah, it's D, because we know to say that we've learned to say that all these, they affect. So once the question is do not affect, meaning there is no correct answer there. Or what we put there, they do what? They do affect. So we can't pick any of those that we get A, B, C. So the correct answer on that instance would be a D. Okay, so now let's try to talk about one of the gels of which we can use. We are now moving, we're trying to talk about the gels, one of the gels we can use. So polyacrylamide gel, polyacrylamide gel. So this can also be abbreviated as what? The page. So when we say the page, we are talking about poly, the P, acrylamide, we have the A, the G, which is for gel, and E, electrophoresis. So it will be like this: polyacrylamide gel electrophoresis. So this is our page. So sometimes you'll be seeing the page there. So when we're talking about the polyacrylamide gel, so this is simply a porous gel that is made up of polyacrylamide. So the polyacrylamide is simply a polymer that does not chemically react with proteins, hence being considered to be very inactive. So it is inactive in such a way that it doesn't react with proteins. So the polyacrylamide gel has many pores and channels that allows the proteins to be moving through, hence it being suitable to be used for what? For separation of these proteins. Okay. We also have another protein, which is the agar and agarose gel electro. So when we are using the agar, we are talking about the name now will change. Remember, for the previous one, we are saying to say that for the acrylamide gel. So now here we are talking about the agarose gel electrophoresis. So for the agarose gel electrophoresis, we are using the agar instead of the gel that we are talking about, instead of the polyacrylamide that side. So when you talk about the agar, so this is simply the mixture of polysaccharides. So it is extracted from seaweeds. So agarose is highly purified and uncharged polysaccharide derived from the agar. So this, when we talk about this agar, it is stable, or it remains a liquid not until it reaches a temperature that is lower than what? 40 degrees. So when this is being prepared, the temperature is more than 40 degrees. Once the temperature reaches 40 and downwards, we are going to observe to say that now this will start what? Solidifying. So this, it consists of a large pores, and the size of the pores is determined by the concentration of the agarose in the gel. So if we put a lot of agarose, that implies to say that the size of the pores will be a bit smaller. If we put just a few, we have a lot of what? The size of the pores will be big. So now, in between these polysaccharides, we have a bond, which is the hydrogen bond, which is, we know to say that it's what? It's a weak bond. So we should always have in mind to say that the bond that is between the polysaccharides in the agarose gel is what? Hydrogen bond. That's very much important. Okay. So now, what are some of the advantages and disadvantages of using polyagarose gel? At polyagarose gel, agarose electrophoresis. So when you talk about the agarose electrophoresis, the gel itself, agarose gel, it's easy to prepare, and only small concentration of agar is required. So if you have that, you'll be able to prepare that, and then you're good to go. So again, the resolution of superior to that of the filter paper. So if you want, because we also have the paper electrophoresis, so when you're talking about the resolution, will be superior when you compare it to that of the resolution for the filter paper. Again, we have the third one here. That's the third advantage, which is the adsorption of negatively charged protein molecule is negligible, and it also absorbs protein relatively less when compared to other medium. So sharp zones are obtained due to less adsorption. Also, the recovery of protein is good, so it's good method for preparative purposes. So it has advantages. We also have disadvantages. This side, where electroosmosis is supposed to be high, the resolution is less compared to what? Polyacrylamide gels. So polyacrylamide gel, the resolution is high. So we've talked about three things now here. We have paper, we have agarose, and polyacrylamide. So of which the resolution is high when it comes to poly, followed by agarose, and then the paper, based on what we've discussed so far. So different sources and batches of agar to give different results, and purification is needed. So once we have different sources of these agar for us to prepare the gel, depending on the source, maybe you may find to say that you need a lot of concentration of the powder for you to come up with a gel, or just a few. So it differs. And apart from that, for us to use it without having challenges, we are supposed to purify it. That's when we can use it effectively. Okay, so now let's go back to the polyacrylamide gel electrophoresis, the gel, the page in short. So so this is actually prepared by polymerizing acrylamide monomers. So remember, for the agarose, we said that it deals with what? Polysaccharides. Here we are talking about now monomers. So acrylamide monomers, they are polymerized in the presence of methylene acrylamide to cross-link the monomers. So they are going to be cross-linked. So now, when we are talking about the agarose gel, we said to say that the bonds that are between the molecules are called what? Hydrogen bonds. But now when it comes to polyacrylamide, we are talking about the covalent cross links. So they are tougher than the agarose gel. So this one is a bit, it's tougher compared to the agarose gel. So this one, it is thermostable, it is transparent, it is strong, and relatively chemically inert. So these are some of the benefits when someone asks you to say that why do you prefer using the polyacrylamide gel electrophoresis compared to the agarose gel, so you can try to tackle these things. So gels are uncharged and are prepared in a variety of pore sizes. So by means of this method, proteins are separated by molecular sieving. So thanks to that, the ability of preparing them in different sizes, molecular sieving is very much possible. Okay, so now when we're talking about polyacrylamide gel electrophoresis, they can exist in various types. So we have the first one, which is the native page, and the second one, which is the SDS page. I remember one was saying that the social and development studies. So now we are going to understand fully what the SDS means. So the native gels are run in non-denaturing conditions. So we'll note the differences between the native gel and the SDS page. So for this one, we are saying to say that they are run under what denaturing conditions, so that the analyte's natural structure is maintained. So the essence of not running these the proteins under denaturing conditions, we want to maintain the natural structure of those proteins. Again, separation is based upon the charge, the size, and the shape of macromolecules when we're using this. So they are also useful for separation of mixture of proteins. This was the origin mode of electrophoresis. So initially this was introduced, and then other methods were being brought in place. So now we are talking about the SDS page. So the SDS page separates based on one, electric field strength, two, charge of the molecule, and three, the coefficient friction. So it is a common method that determines the molecular weight of the protein, and it is very much useful for checking of purity of proteins. So once you want to check the purity of proteins, so this is the recommended method to use. Okay, so the native page, let's try just to talk a bit about the native page electrophoresis. So the native page electrophoresis, um, the gel is has different pore sizes that are cast into the column inside the vertical tubes. That's diagram we had drawn earlier. So even with large pores, gel at the top and the small pores at the bottom. So the way it is designed in such a way that the large pores will be put on top and then the small pores will be put at the bottom. So as now we are moving, the molecules are moving depending with the sizes of the pores they are finding. So now the movements now will be different. Those with that are big, and once they find the smaller sizes in terms of the pores, there will be a frictional force now being produced, and the velocity, remember what we talked about, that the frictional force can also affect the velocity of the molecules. So microgram quantity of the sample is placed over the top of the gel column and covered by the buffer solution having a pH so as to change the sample components into anions. So remember, we said to say that when we are dealing with electrophoresis, there is electric field that is supposed now to bring about the movement of molecules moving, where it's negative recharged, it moves towards the positive, and the positive move towards the negative. So in this context, there is no nurturing, there is no anything that is in place apart from the buffer solution. So this buffer solution has a certain pH that brings about, once it comes into contact with a protein, the proteins now will be charged. They will become anions. So the foot of the column is made to dip uh, in the same buffer in the bottom reservoir. So when we talk about the cathode and the anode are kept above and below the column. So the cathode, you know that these are negative recharged, and the anode, they are positive recharged. So they will be kept one on top and the other one the other one just down at the bottom. So when the electric field has been applied, the molecules will be moving. Those, if the positive recharged are put down, those other negative recharged, they will be put downwards. So here already we are having a picture to say that once this buffer has been put, the proteins will be the charge for the proteins now from neutral will change into towards negative charge, so that they start moving downwards. So macromolecular anions move towards the anode down to the gel column. So I've already mentioned about this. So the second point, which is there is no external solvent space. So all the migratory particles have to pass through the gel pores. So now here is the difference. When we talked about the gel filtration chromatography, only small molecules, we mentioned to I know to say we've researched to say that small particles will be moving now through the pores, and then those large molecules will be moving using another space, the solvent space. But now when you talk about this method, all the molecules will be forced to move across through the WCC, the pores. They do not move using any other space. So now the rate of the migration depends on the charge and the mass ratio. The charge and mass ratio are very important when it comes to uh, the movement of these particles. So we are going to see now how that will be affected. So if So if we've put now different sample components, they will get to be separated into discrete migratory bonds along the gel column on the basis of electrophoretic mobility and gel filtration effect. The gel filtration effect will be in place, and the electrophoretic mobility will also be in place. Okay, so now we are talking about the SDS. What is the SDS page? So we'll briefly now try to explain what the SDS page is. So the SDS page is the type of a gel that is um, where now it involves the usage of the SDS, which is the sodium dodacyl sulfate. So not the social and development studies, but the sodium dodacyl sulfate. So the name now will change. It is now, since we are using, there is an additional molecule that has been introduced, the sodium dodacyl sulfate. So it will change to sodium dodacyl sulfate polyacrylamide gel electrophoresis. So this is a technique that is widely used in biochemistry, forensics, genetics, and molecular biology to separate proteins according to their electrophoretic mobility. So the SDS page separates proteins by what? By size. So the sample protein. So now, before we put in those wells we had discussed earlier, here is what happens. The sample protein will now be put into a denaturing solution. So now here is the difference now between the SDS page and the native page. So the native page, there is no need of using the denaturing solution. So now when we are using the SDS page, we are going to use the what? The denaturing solution. And that denaturing solution consists of what? The SDS, which is the sodium dodacyl sulfate, anions, and the mecaphoethanol. So now, how will now this be helpful? So remember, we are saying that the SDS is an ion, so it is going to be giving a charge to proteins. So the first thing it's going to do, it's going to break the covalent interaction of proteins. So maybe a protein will be like this. This is a protein. So this is a covalent interaction of a protein. So it's going to cut, removing this part. A protein will remain like that. So once that is happen, or once that happens, that's when now the SDS again, it's going to attach to this protein. So imagine this is the SDS. It's going to attach to this protein. So once it attaches to this protein, so remember earlier on we said that this SDS is what? An ion. So it's negatively charged in another ways. To make, yeah, it's negatively charged. So since it's negatively charged, it's going to get its negativity and render it to what? To a protein. So we're expecting once this SDS anion attaches the protein will be what? Will be negatively charged. So now we are going to form a complex. The SDS and the protein will form the SDS protein complex. So now this SDS protein complex will now be moving down the gel. So they will be dragged down by the electric field that is being produced since we connected the device to the what? To the source, which happens to be the battery in this case, which is providing the constant what is electric field. So since they are all negatively charged, remember what we said? Downwards below, they're supposed to be what? Positively charged. They will all now be forced to move what? Downwards. All the proteins, they will be forced to move downward. Okay, so now here is the most now important thing we need to understand. So since we have been singing that separation happens based on the size, what happens? Larger proteins move more slowly because they experience a greater friction than smaller proteins. Therefore, larger proteins will be higher up along the slab than the smaller proteins. So now, here is the thing we need now to put in mind. Listen, listen. So this is like a small protein, and this is a large protein. Remember that once they are inactivated by SDS, the SDS attached to this. So what happens is one SDS will be attaching to this. So if this is like a small SDS protein, we are expecting only a few SDS to attach to this. So the ratio of attachment, it's one amino acid will be attached by what? To SDS. So a protein is made up of a number of amino acids. So once we write a protein to be like this, we are having a lot of amino acids here. So one amino acid will be attached by 2 SDS, making now this protein to be having a lot of SDS like that. They will be attached like that, a lot of them. So if at this point we are able to remember one of the factors that will bring about the the movement of that will affect the movement of the protein, we mentioned the charge. So now this one will be highly charged compared to this one. So if this is highly charged, we are expecting the frictional force to be more, to be greater to compared to this one, which is having only a few charged particles attached to it, hence bringing about the smaller molecules to move faster compared to the what? Larger molecules. So always have in mind, different sizes of proteins have different channels. So depending on the size of the protein, remember we said to say that there are various sizes in terms of the pores. So they'll be having different channels where those now proteins will be using maybe to migrate for us to have a successful separation. So now this is what I was trying to mention. Imagine we've gotten a mixture of proteins now put in those wells. So the colors here we're having on top on this first diagram, the green one it's a protein, the I don't know, this one is should be orange, it's a protein, and these that are seemingly to be a bit purple or blackish, they are also proteins. So now they are moving. So once we apply the electric field, so this is the initial placement, the proteins are on top here. So once electrophoresis has taken place, remember we said to say that smaller molecules will be moving downwards faster than the bigger molecules. So smaller molecules will move downwards, followed by these molecules that are a bit bigger than these, and then the largest molecules now will be on top. So in this case we can tell to say that separation has taken place. So in case you would like to research more on electrophoresis, I've just put the references acknowledging where all the information was gotten for you guys to benefit, and I'm certain that by now you've benefited. Remember, if you have any question, you are free to ask, and I'll be more than glad to attend to your questions. Thank you very much. Thank you very much for your time and for your attention.